dear interested one. The full video I'm indebted to Ian Scott, President and Chief Scientist at Moltex Energy Limited. Moltex, or better Ian Scott, emphasizes cheap and safe. The question to ask is, how can a nuclear power plant be cheap? Cheaper than a coal or a gas plant and still be safe? Well, everything has to do with the fuel and the water that serves as a coolant and a moderator. This graph shows the cost of capital from one day to the next. After 1983 and the problems of Chernobyl in particular and 3 Mile Island, the cost shot up because of additional passive safety devices and additional containment buildings plus safety devices on safety devices. And today the cost ran up to 7,000 to 8,000 euro or dollars per kilowatt, which is just not feasible. This is still much cheaper than wind farms, but since global CO2 emissions are not determined in Europe, but rather in the emerging countries like China, Africa, India, etc., we will need to design cheap, automatically controlled, and inherently safe nuclear power plants, and cheaper than coal-fired power plants. Otherwise, those countries will grow in wealth by building coal power plants, just as we have done. And by the way, this process is in full swing and thousands of coal power plants are planned. The key to eliminating the danger of nuclear reactors is actually using a molten salt at atmospheric pressure instead of water at high pressure with solid vulnerable fuel pellets.
And our belief that the only way that we will really combat climate change is by making fossil fuels unattractive economically. In other words, we need to find sources of energy that are cheaper than burning gas. You can't have a system that's 100% renewables. If all we had was wind turbines, we would need the most enormous amount of energy storage for all those times when there is no wind, and massive overcapacity for when there is some wind, and the costs of that simply don't work.
On the figure we see a principal diagram of our current nuclear power plant. In any kind of power plant, the idea is to heat water to steam. Steam is then used to drive a steam turbine, which in turn turns a magnet around a coil of copper wires, in which electricity is generated, just like our bicycle dynamo of earlier times. So all the coal power plants, gas and oil power plants burns fossil fuel to generate heat. And in the figure on the top, you see a gas molecule that we burn with oxygen, creating CO2 and 9 electrovolt heat. Sorry, that electrovolt is a much smaller unit of the kilowatt hour. Burning coal, oil and gas also creates a lot of fine dust and harmful emissions gases with mercury, arsenic, lead and many nitrogen oxides. We just throw them into the environment. In a nuclear power plant, we bombard large atomic nuclei, uranium nuclei, so that is split in two, and generate millions of times more heat than burning a fossil molecule of gas, coal or oil, without releasing anything harmful into the atmosphere. With nuclear energy, no CO2 is produced, but radioactive fission elements, in our example xenon and strontium, and a few neutrons that continue the nuclear reaction. In other words, radioactive waste that remains in the nuclear reactor and does not enter the environment.
All nuclear today is safe. The way nuclear today has got safe is by spending an awful lot of money to make it so. What we do is take away the hazards so that you don't need that level of extreme engineering to make it safe.
The key to eliminating the dangers of our current nuclear reactors in an inexpensive way is actually replacing the water with molten salt. First, let's look at our Belgium nuclear reactors in a simple way. So we see a large vessel with small sealed tubes filled with solid uranium pellets. Inside you can see it red-yellow, surrounding by cooling water at high pressure and temperature. Normally, water boils at 100 degrees Celsius, but by increasing the pressure through the pressurizer, you can see it on the figure, to 150 bar, this cooling water is allowed to reach over the 300 degrees Celsius without boiling. This means, of course, that the entire primary circuit, the reactor vessel, the tubes, the primary pump and the primary heat exchanger, is pressurized with superheated water that wants to turn into steam. So if there is a leak in the primary circuit, you get a steam explosion. Hence the large, highly reinforced concrete containment building around the reactor. But what if we replaced that water with a salt mixture? The salt mixture becomes liquid around 400 degrees Celsius and boils around 1400 degrees Celsius. This means that we should not put that liquid salt mixture under pressure. Atmospheric pressure is okay. And we have a margin of 1000 degrees Celsius between which we can work. The reactor vessel does not have to have walls 25 centimeters thick. Also, the entire primary circuit can be done much cheaper. So a leak can no longer cause a steam explosion. In the event of a leak, the salt will simply solidify on site and certainly not end up in the atmosphere. There you go, problem 1 solved, with much less expense. And now for the fuel rods. This consists of uranium compressed into pellets. Tubes filled with pellets of uranium, so solid fuel pellets, and multiple tubes are brought together to form a bundle of tubes. That bundle of tubes, in which the fission takes place and in which the heat is generated, is shown here colored red-yellow. The fuel, uranium, in other words the highly radioactive content of the tubes, does not come into contact with the coolant in the primary circuit. So, no radioactive material is pumped around in the primary circuit, the reactor vessel, the tubes, the primary heat exchanger and the primary pump. However, because an enormous amount of heat is released during the fission of those uranium cores, those pellets threaten to expand and burst. After 4 years in the nuclear reactor, they even threaten to damage the walls of the tubes. This must be avoided at all costs. Otherwise, the radioactive content of the tubes will end up in the coolant as well in the entire primary circuit. This means that after 4 years we are forced to remove the fuel bundles from the nuclear reactor. So we have to shut down the reactor all 4 years, open the reactor vessel and replace the 4 years old fuel bundles with new ones. So the old fuel bundles are safely put away as radioactive waste. Even though those fuel bundles are only 4% fissioned. Indeed, you hear it right. Our Belgian nuclear waste is still 96% fissionable, so pure fuel for our molten salt reactor, which I'll explain here step by step. Well, the problem of those pellets bursting prematurely, we are going to solve in any case also with a liquid salt. We are not going to press the uranium powder into solid pellets, but dissolve it in a salt, so liquefy it. And we will pour that fuel salt mixture into stainless steel tubes that are open at the top. See on the figure on the left. Then those tubes can no longer be damaged, and the radioactive content of those tubes also does not come in contact with the coolant salt. All fission elements created by fission of the uranium nuclei are directly bound with the salt. So the radioactive fission elements like cesium and iodine remain nice and safe in the tube. They are not longer gases, but liquid salts. Now the primary purpose of our Belgian nuclear waste is to dissolve it into a salt liquid and pour it into those stainless steel tubes.
Two elements are formed as a salt. They're very chemically stable.
Yeah, there's nothing in the world more stable than fluorides or chloride salts. They're just impossible to kind of split apart.
In this way, this waste burner can split our nuclear waste until all the large nuclei are split. And then all that remains is nuclear waste shrunk 100 times in volume and stored for only 300 years instead of 300,000 years. Who can be against this? Realize that with it already existing waste, the size of a soccer field and half a meter high, Belgium can continue to produce electricity and develop process heat for our industry for 1,000 years. This will reduce our waste mountain from half a meter high to 5 millimeters high, and we will only have to store it safely for 300 years or so. Here you see a figure with the many fuel tubes, filled with uranium salt or with the Belgium nuclear waste. Around those tubes there is plenty of room for another salt solution to flow as a coolant. Be aware that this coolant salt flowing around the tubes and into the entire primary circuit does not contain fissile material. And finally, the shape of the nuclear reactor changes. See figure. A group of fuel tubes, fuel assembly or fuel group, can be replaced via the vertical elevator valve while the reactor is at power. So another advantage over our current nuclear reactors. A fuel assembly that is taken out and then replaced is moved to the periphery of the reactor tank. There, they stay for up to a year and then are removed as a group through the reactor airlock into shipping containers for storage. And here you see another figure of the nuclear reactor. The red in the center are the many stainless steel tubes filled with a liquid fuel salt. Essentially, the reactor core of the stable salt reactor is a closed boiling pan, only half filled with molten salt coolant that does not come in contact with the fission products. The liquid fuel, so the fissile material or the nuclear waste, is nicely enclosed separately in a series of stainless steel tubes. See in the center, red. The blue tubes in the outer area are the boiler tubes that extract heat from the reactor core. These tubes and the core, separated by a ring of flow baffles that create the flow path, works together to create a convection flow that does not require additional pumping, but circulated naturally and extract heat from the core. So one makes sure that the cooling salt, through natural circulation, distributes the heat nicely over the entire reactor vessel volume. In summary, the reactor is like a stainless steel cooking pot, half filled with a liquid hot salt, minimum 385 degrees Celsius, otherwise it will solidify, and maximum 1400 degrees Celsius, otherwise it will boil. For the time being, we will limit the temperature to around 650 degrees Celsius, but it is only due to the metal alloys of the vessel and the tubes in the vessel. The reactor heat developed is transferred from the reactor vessel through the reactor coolant salt, through the primary pump and the primary heat exchanger, to a secondary heat exchanger located outside the nuclear reactor, and to go from there to store heat via another type of salt in multiple heat storage tanks. I call it giant thermos bottles. That other kind of salt in those thermos bottles or containers, that's actually a salt that has long been used in concentrated sun power systems, a proven technique that stores heat from concentrated sunlight in a liquid salt. But be aware that such a giant field of mirrors is very sensitive to storms, sandstorms, and pollution generally. So, outside the nuclear part is a multitude of thermal storage tanks filled with a salt solution in which electrical energy can be stored in form of a hot salt. So this is energy to be used later at peak time or to smoothly and accurately adjust the flakiness of wind turbine energy. So storing energy becomes possible with this reactor, and up to 3 times cheaper than with the cheapest batteries. So this reactor has a closed fuse cycle, is intrinsically safe, without the need of additional designs, and has few problems with licensing. It is made up of components of which all the intrinsic properties have long been proved. Most importantly, it produces cheaper electricity than gas or coal-fired plants. Indeed, it is all about money.
Where does your certainty come from that what you're putting forward really has that contribution to make?
It's driven because it's a reactor that can be built at a lower cost than a combined cycle gas turbine power station. Simple as that.
This kind of nuclear power plant that makes cheap electricity and convert our existing long-term radioactive waste into only 300 years of storable waste is ideal for a country like Belgium, but also for the emerging countries. To achieve netto zero emissions globally, every aspect of modern life must be decarbonized. And here you see on the figure an arrangement with two 300 megawatt electro modules that provide both industrial heat, for example for a cement or a steel industry, but also heat water, so that an electrolysis plant to make hydrogen works with a better efficiency. Also, electricity is produced in this setup to power the hydrogen plant, etc. Be aware that making electricity only represents about 20% of our total energy consumption. Solutions are needed for heating our buildings, now with gas and mazout. For heavy industry, steel, cement, aluminium, chemicals, glass, fertilizer plants, and transport by land, air, and sea. Therefore, all our nuclear power plants must be safely given life extension of at least 20 years. 40 years is also possible. And additional modular nuclear waste burners must be steadily added to decarbonize industry and transportation and make us independent of rogue countries in terms of energy, and to steadily phase out fossil fuel and replace it with cheap energy for rich and poor. Also be aware that not a single Belgian nuclear power plant is cracking, or that there is anything going on with the reactor vessel wall that poses a danger. That's fake news. The vast majority of society's non-electricity needs are currently met by fossil fuels because these fuels are cheap and available everywhere. Hydrogen is a potential alternative to fossil sources, but it is only as clean as the energy sources that produce it in the first place. So the stable salt reactor provides a way to produce clean, inexpensive hydrogen. Because it generates a large amount of heat, the SSR can support ultra-efficient hydrogen production processes with no CO2 emissions and at a lower cost than oil or gas. It means that hydrogen no longer has to be green or cheap. Now it can be both. The hydrogen economy has the same economic requirements as electricity generation. For the energy transition to happen in time to help the climate, clean solutions must be cheaper than the dirty ones. And people with access to cheap energy benefit from a better standard of living. Cheap and readily available electricity can lift people out of energy poverty. Even in developed countries, there is a clear link between electricity prices and the quality of life. And so the stable salt reactor is simpler and smaller than other reactor designs, making it less expensive to build and operate. So the stable salt reactor is passively safe, meaning that no human intervention is required to shut it down in an event of a problem. And much of the SSR safety case comes from the fact that there are no hazards in the first place. And so, the most dangerous fission products are salts, not gases. So there is no risk of them entering the atmosphere under any circumstances.
Salt as a fuel, on the other hand, it is possible to operate at very high temperatures, yet still at low pressures.
Nothing's trying to really burst out. You don't use water in the reactor so that there's no possible steam explosion, and there's nothing that can make a chemical potential.
And the fission reaction slows down as the temperature rises, so the system is self-dampening. Because the SSR is simpler than other reactors, it is also smaller. At a fraction of the size of a conventional reactor, the SSR requires fewer parts and less work to build.
The International Energy Agency every year do a forecast of what the power production in the world will be over the coming 20-30 years based on what's actually happening, what governments say they're doing. And their projection is that coal burning will stay at the same level it is today, not fall at all, and that gas burning will double. That's a catastrophe, absolute catastrophe for the planet.